Welcome back to another episode of Studysmart. In today's video, we are going to be talking about the operator D method of solving the non-homogeneous equation. In our previous videos, we've talked about several methods, and then we are now in the next method, which is the operator D method. Right. So under this operator D method, we'll be talking about the operator D method itself, and then we are going to be talking about the inverse operator D. Inverse operator D. Alright, so the operator D method of solving the non-homogeneous solution of an ODE, right? It requires some basic steps also, just like as I've given in the previous videos. I've given you step-by-step guides on how to go about the previous steps. So I'm going to do the same here, just for you to understand the properties and the basic properties governing this method. And then if you have understood the basic properties governing this method, then you are good to go with this method. Right. So subsequently um, taking we'll be taking different videos on different properties of this method, taking different examples concerning each of the properties in this method. So don't forget to hit the subscribe button so you don't miss out on this. Right, so we are going to be starting with the operator D itself. Right, so the operator D, just as the name implied, operator D. So this D here will represent d over dy by d. What it means is that in operator D, we don't write dy over dx. Right, so even if you want to write dy over dx, but in using the operator D method, you express it in form of dy. Right, so this represents dy over dx. Why this d itself represents d over dx? Right, so it means that if I say dt applies or means that this is dt over dx. Right, so the d itself, it's d over dx. What I mean is that the function d itself means d over dx. So this is what it means. So anything can be here, right? So the function can be, the expression can be in terms of y, in terms of t, in terms of m, and so forth, right? So just bear in mind that d in operator D method implies d over dx, right? So in the operator D method, we majorly deal with differentiation, right? So while in the inverse operator D, we majorly deal with integration, right? So as the video progresses, we'll be drilling on each of these operator D and how they all work, right? So we're going to be starting with the operator D itself before moving into the inverse operator D, right? So I'm going to give you some basic properties that concerns this operator D, how to go about such problems when you see them. Right, some basic properties of operator D method. Basic properties of operator D. Right, so the first property there, if you have, let me say A, if you have an operator D, that's d over dx of the function lambda u, lambda u of x, this implies that, or this means that I'm going to have lambda d of u of x. So as the video progresses, we are going to be taking examples on each of these um each of these properties. Right. So the second property is if you have d to the power a times d to the power b, right, as a function of u of x, right, this implies that, just from the law of indices, we know that if you have two same bases, and then different powers. You take one of the bases and sum of the powers. Right, so this is going to be d to the power a plus b all in u of x. Right, so that's the second properties of operator d. Right, the third property there, if I have d of u of x, right, if I have d of u of x, let me just say here plus v of u of x. Right, so it implies that, or it means that I'm going to distribute d to each of these functions. Right, so if I distribute d to each of these functions, I will be having du of x plus d v of x. Right, so these are the basic properties of operator d. Right, so we'll be taking some few examples in order to illustrate and know how to use these properties. Right, so because you will need all these properties in terms of applying it to solving the non-homogeneous ODE. So you need the basic idea of this part in order for you to dive into solving the non-homogeneous ODE. Right, so we'll be taking some few examples. For the first property, let us take an example. Right, so example, if I have the square into 3x to power 2. Right, so let us solve this. Just like I told you earlier, in operator d we differentiate, but in the inverse operator d we integrate. Right, so you need to take note of all these things in order for you to know how to go about this. We have the operator d method, and inside the operator d method we have the inverse operator d method. So this will be the inverse operator d method. Alright, so we have the operator d and we have the inverse. Don't forget, in the operator d we differentiate. In the inverse operator d we integrate. Right, so this is an operator d, it's not an inverse. Alright, it's not an inverse because I said that in operator d we differentiate. This means that I'm going to differentiate this expression twice. Right, so it implies that this is d over dx because it is a function of x into d over dx of this particular function, which is 3x squared. Right, so this is what it means. This is what this whole stuff is talking about here. This is what it means. Right, so if I differentiate the inner one first, I'm going to have d over dx. So if let me differentiate this one, if I differentiate 3x to power 2, I'm going to have 6x. Right, so this here will give me 6x because these two will have to come down, reduce by 1, and multiply the expression. So that 2 times 3 here gives me 6x, then reduce the power by 1, which is 1. Alright, so I still have another thing to differentiate here, right? So I'm still going to be having the differential of this, which is going to give me 6. That becomes the answer to the problem, which illustrates the first property of this operator d. Right, so we'll be going into the second properties. Alright, so second example, if I have let me see, if I have d squared times d to power 3 of the function 6x to power 2, or maybe to power 3. Okay, let me leave it to power 2. Right, so from the second property we said that d to power a times d to power b of u of x. Right, so the u is this, is my 6 here. That's my u. Right, so it implies that I'm going to sum up the powers, take one of the base, and then I'm going to differentiate. Right, so following these rules, following these properties, I can just say over here, recall the property that d to power a times d to power b of the function u of x is equal to d to power a plus b for the function u of x. Alright, so this implies that in this place my a is equal to what? 2, and my b is equal to what? 3. So I'm going to sum up a plus b, which is 2 plus 3, to get the number of times I'm going to differentiate this expression. Like I said, don't forget, if you have an inverse operator d, which means 1 over the d itself, it is in this form, 1 over d, this is 1 over d, inverse. It means that you are going to integrate, right? So if you have only d, which is not an inverse, you are going to differentiate. Take note of that. Differentiate when you have d, or integrate when you have the inverse. All right, so take note of that. So we are going to make use of this property. So if we do so, from this our expression, I'm going to have d to power 2 plus 3 here, times this is a function of 6x squared. So this is going to give me 2 plus 3 here will give me 5. So I have d to power 5 into 6x squared. Alright, so what this means is that I'm going to differentiate this expression 5 good times. Alright, so it means that I will start by differentiating d to power 4 over the x to power 4 into, I'll differentiate first one. Alright, so I'm going to differentiate first one, d over dx of this whole expression as 6x squared. So if I differentiate 6x squared, I'm going to have, this remains d to power 4 into the x to power 4 into, right, so if I differentiate this, 2 times 6 here gives me 12, and I have my x. So if I've done that, that means I'll be left with this, right? So I'm going to differentiate again. I'm left with 4 differentiation. So I'm going to differentiate again to get d to power 3 over dx to power 3 into d over dx of this expression, which is 12x. Right, so I'm going to differentiate this again to obtain d to power 3 over dx to power 3 into, so if I differentiate 12x here, gives me 12. So here will be 12. I still have 3 times differentiation here. So I'm still going to differentiate this function. I'll differentiate to have 2 squared over the x to power 2 into d over dx of 12. Right, so this expression now, if I differentiate the inner one again, I'm going to obtain the square over the x to power 2, right, into, if I differentiate a constant, it gives me 0. Right, it means that I'm still going to differentiate again. So I'm going to differentiate this again to obtain d over dx of the function 0. So if I do that, I'm going to obtain this to be equal to d over dx. Of course, 0, if you differentiate 0, you still get 0. Alright, so if I differentiate this again, I'm still going to get 0 as the answer. Alright, so the whole idea of this is that, right, from the first example we did, we got d to power 2. It means that this is the square of this function over the x squared. I repeat again, this is the square y over the x squared. Alright, so this is the square of this function over the x squared. So this is the second derivative. So it means that I'm going to differentiate this function twice, which we did here to obtain this. Following the first property, the second property, we are using it to illustrate this now. Right, so this is d to power 2 times d to power 3 of this function. It means that from the properties I gave you, d to power a times d to power b of the function, I said that you are going to take one of the d's and then add up the powers to obtain this. It's the same thing we did here. Our a here, which is the first exponent, which is 2, the second exponent, which is b, which is 3, we added it up to get the number of times we are going to differentiate. All right. That's for the second properties that I gave. It is this. All right. So we have the next property. Let's just take an example about that. If I have an expression d into, let's take q of x to be um exponential, let's take q of x to be exponential, let's take q of x to be exponential 2x, right? Then plus v of x to be sine 2x, right? Is an example. So now looking at the third rule I gave, the third property rather that I gave, I told you that if d is a function of u of x plus v of x, it implies that I'm going to distribute d to each of the functions, right? So it means that I'm going to distribute d to this. It's just like opening bracket. I will use the d to open up the bracket to obtain this, right? So considering the the third property, I can just say here, recall that d into u of x plus v of x, right, is same thing as having du of x plus dv of x, right? So where my u of x and v of x is this and this, right? So this first function here becomes my u of x, and sine 2x here becomes my v of x. So following this property, we are going to be solving this problem here, which implies that I'm going to distribute this d to each of the functions here. It means that I'm going to be having d exponential 2x plus d sine 2x, right? So you having this now, right? You having this, just like I said earlier, if you have something like this, if you have something in this form, the d, you have to differentiate. It means that here we are differentiating just once, right? We are differentiating once. Assuming this is an inverse, let me say 1 over the d of this. That means I'm going to integrate this, no longer differentiate. All right. So it's good you understand this. It's good you understand that in d in d itself, when you have d, you differentiate. But if you have the inverse of d, which is the inverse operator d, you integrate, right? So if I differentiate this, I'm going to have 2 exponential 2x, because if you've been watching my previous videos, I said that I gave a simple trick of differentiating an exponential function. I said that if you want to differentiate an exponential function, consider the coefficient of x here, pick out the coefficient of x and then multiply it by the whole expression here, right? So this is d over what? D over dx of this function. So let's just write it as d over dx of this function, which implies that this is the function is exponential 2x, then plus d over dx of this function, which is sine 2x, right? So we are going to differentiate this function now. If I differentiate this, I'm going to be having this to be equal to, so the coefficient of 2x here is 2. I'll pick out the coefficient of 2x and then multiply it by this whole expression. So I'm going to be having 2 exponential 2x, right? So if I differentiate this function, I'll pick out this one also, differentiate sine x, and then multiply it by the coefficient of x here. It means that this is 2, all right? This is the 2 here. Then I will differentiate sine x here, all right? So if I differentiate sine x, I will have cos x, cos. So I'll still have the 2x. Then since I'm differentiating sine x, and if I differentiate sine x, I'll have a positive cos. So this becomes plus here. It implies that if I have cos 2x, if I want to differentiate cos 2x here, I'll pick out the 2 here and then multiply it by the differential of cos x. So the differential of cos x here is minus sine x. So that's what this whole idea is all about, right? So from these few examples, you've used these few examples to illustrate the basic properties of operator D, right? So that's just the basic properties of operator D. In knowing these properties, you'll be able to tackle problems on it. It's as simple as that. Right. So next up here, we're going to be discussing the inverse operator, which is our major area of concern. Right. This is our major area of concern. So I'll just come over here and then I'll put inverse operator D. Inverse operator now becomes 1 over, this becomes 1 over D. Right. So 1 over D. At this point, like I said earlier, in inverse operator, you integrate. You integrate at this point. In operator D, you differentiate. In inverse operator D, you integrate. Right. So just like we have right. So in operator D, you differentiate. In inverse operator D, you integrate. Right. So I'm going to give you again another property. It's good you know the properties, because with the properties, it becomes as easier as possible for you to solve them. So some basic properties in inverse operator D. Right. So properties of inverse operator D. Right. So this is inverse operator D, 1 over D. Right. So firstly, if I have L into D, right, then exponential, I've used lambda in the other part, so I can just use another constant. Let me use nx here. Nx. Right. So I'm going to have, from this property, I'm going to replace D here by N. It means that this property becomes L into N, right? And I still have this function, exponential nx. If you see something like this, all you just need to do is replace the D by this, and then repeat every other function. Right. Second property, if I have L into D, and I have exponential nx, then u of x, right? On u of x, I'm going to have, what I'm going to do in this case is that I'm going to replace D here. I'm going to replace D, right? The idea here is very simple. At this point, I'm going to add n to D. I'm going to add n to D at this point. So it means that I'm going to be having exponential nx here. Then I have I'll have D. Then I'll add n plus n, right, to it. Then I'll have u of x. U of x. That's what it means. All right. If I have L of D of this function, it means that I'm going to add n, which is n here can be any number. All right. N here can be any number. N here can be 2, it can be 3, it can be 4, it can be 5, it can be even any number. All you just need to do is to take that number, then add it to the D. All right. Add it to the D. Then this is what you have. All right. So the next property, we are going to be taking examples in order for us to illustrate this. Right. So if I have L into D squared, maybe cos nx here, I'm going to be replacing D squared here by minus n squared. Right. So L here becomes, this is minus n squared, and I still have my cos lambda x. Right. So this is what it means here. That's for this. For this, if I have L to D squared, the idea here is just very, every other thing here is the same. The major idea, the whole idea here is just that I'm replacing D squared by minus n squared, where n here can be any number. All right, n can be any number. So the last property, if I have L into D squared for sine n squared, I'm going to have it to be same as well. So this is L into minus n squared sine. All right, so sorry, this is n. Sorry, this is n. I have nx, where n can be any number. Nx. All right, so where n can be any number. So we'll be taking some few examples in order for us to illustrate this point. In order for us to illustrate this point. All right, so for the first example, if I have all right, so this is example. All right, so if I have L, all right, if I have L into 4D squared plus 2D, then plus 3, and then I have exponential 2x here. All right, so if you can check very well, this expression illustrates the first property here, right? All right, so we are going to be writing this in another form. So if I write this in another form, following the properties, so you can follow the property, say recall the property, recall that L of D exponential nx, where I said that n can be any number, is equal to L of n exponential nx, which means that here my n is 2, right? Here my n is 2. Right, so it means that anywhere I see D in this expression, I should replace it by 2. All right, I should replace it by 2. That's what it means. So I'm going to be having L into, all right, this is 4, and my n here is 2. All right, following the rules, n here is 2. So I'm going to be having 2 squared, then plus 2 into 2, and plus 3. I still have my exponential 2x here. All right, so this becomes L into 4. This is 2 times 2, which is 4, plus 2 into 2 plus 3. I have exponential 2x. All right, so 4 times 4 here gives me 16. Then 2 times 2 here gives me 4. I have plus 3. I still have exponential 2x. So I'm going to be having, this becomes, all right, so 16 plus 4 here gives 20. So 20 plus 3 gives 23. So the answer of this problem is 23 exponential 2x. Right, so we are only using this to illustrate each of the properties, so that when we dive into the major when we go into the major use of this operator D in solving a non-homogeneous equation, you don't get confused. Right, you don't get confused. Right, so second, this is for the first property. Right, so for the second property, if we have an expression of the kind, all right, so okay, what if we have another example? Let me use another example to illustrate this point. All right, so what if you have another example, 1 over D minus 2, 1 over D minus 2, then you have exponential 3x here. All right, so you can see that this also relates to the first if I want to rewrite this thing using the rules here, I'm going to be having L, all right, of D here, all right, to exponential 3x. All right, so my D now is in inverse in this point, all right, is in inverse, just like I said earlier. the major thing here is to understand the properties. By the time you understand the properties, and it becomes very easier for you to tackle, right? So the major thing here is, just like I said, replace d by n. In this case here, my d is 3, so I just have 1 over d minus 2 here of exponential 3x. All right, this now becomes 1 over, replace d here by 3, gives 3 minus 2. You still have exponential 3x here. Then this becomes 1 over 3 minus 2 here gives 1, right? 1. I have exponential 3x. So it becomes what? Exponential 3x. And still the answer is still the same thing. All right, so for the next properties, let's take an example on that. All right, so for the second one, if I have let me say d squared plus 2d, all right, then plus 2 here, and I have exponential let me say 2x, then x to power 2, x to power 2. Right, so following the second rule here, you can say recall from the second properties that if I have LD, then exponential nx, LD exponential nx, then u of x, it implies that I'm going to have exponential nx, then I'm going to add n, all right, to the d to have d plus n to obtain, all right, to multiply d of x. So if I follow this principle, or this so if I follow this process, I'm going to be obtaining this. All right, so from here, let's separate our u of x first and our n. All right, so from this point, our n, from this question, our n is always that coefficient of this exponential coefficient, the coefficient of x at this point. So our n here becomes 2, while our u of x becomes x to power 2. All right, becomes x to power 2. So how do we tackle such problem? All right, so how do I tackle such issues? I told you that from these properties, I'm going to add n to d. Right, so if I do so, I'm going to be having my d square here becomes d, all right, plus n squared. Right, so this point now becomes d plus n squared, right, plus 2 into d plus n plus 2. I still have my exponential 2x, then x squared. Right, so at this point now, let's see how we can distribute these functions here. We can come over here to write exponential 2x, then into d plus n squared, right, plus 2 into d plus n, then plus 2. Then we'll drop x squared here. Right, so our n here, we know our n here to be what? 2. So we can say exponential 2x here becomes d plus 2 all squared plus 2 into d plus 2, then plus 2. I have x squared here. Right, so let's stop here. I'm going to open up this bracket, open up this one, then I'll let me see what I have. Right, so if I open up this bracket here, I'm going to be obtaining exponential to 2x. Right, so this becomes d plus 2 times d plus 2, because it's appearing twice here. Then I have 2 into d plus 2, then plus 2, x to power 2. Right, so at this point, I'm going to be having exponential 2x into this times this here gives me d squared. Right, so this times this gives me plus 2d, this times this gives me plus 2d, while this times this gives me plus 4. Then I have this times this gives me plus 2d, this times this gives me plus 4, then plus 2 into x squared here. So I'm going to have exponential 2x into plus 4, which is 8. Then 8 plus 2 here gives me 10. So this becomes 10. Then still have my x squared. So I can multiply this whole expression by x squared here, right? So this becomes if I multiply this by this whole expression here, I'm going to be having exponential 2x into d squared x squared, right? Plus 6d x to power 2, then plus 10 x squared. Alright, so I told you initially that if you see d, you differentiate, but if you see 1 over d, you integrate. So at this point now, what we are saying is d, not 1 over d. So it means that we are going to be differentiating at this point. So now from this point, we're going to be having exponential 2x. So I will differentiate this first. If I differentiate x squared once, I'm going to be having d 2x. Right, I differentiated once here. I'll have this. Then plus I'm going to differentiate this to obtain 2 times 6 here gives me 12. I have 12x. Then plus 10x to power 2, because there's no d here, you won't differentiate. Right, so from this point I still have a d, so I'm still going to differentiate. I have exponential 2x into, if I differentiate this, I will have 2. So this becomes 2. Alright, plus 12x plus 10x squared. Alright, so I can rearrange this to become exponential to power 2x into 10x squared plus 12x plus 2. Alright, so this becomes the answer. Alright, so let's quickly take an example for the cases where we are going to be having the inverse part of this thing. Right, so instead of seeing this, we are going to see an inverse where we are going to integrate so that we understand more. Right, so let us take another example. Let's say another example. Let us just say the inverse of d squared minus 4d maybe plus 2, right? So let us have this. Then let's have the functions exponential 2x, then maybe x to power 3. Right, so let us do this. Let us solve this using the same approach we used initially. But at the end product, you are going to be having the inverse of the d operator so that we can integrate. Alright, so firstly, right, so if you see such kind of question, how do you tackle it? Right, so using the idea you've known from the initial one, you also recall from the rule. I told you that if you have Alright, so looking at this question, you see that we have two functions. We have exponential 2x and we have x cubed, which satisfies one of the properties. Alright, so let's go back to the properties and check. Alright, so if you look at the property, you understand that we have from property 2, this property here, we have two functions. We have exponential to nx and then u of x. This u of x here is the x cube here. Right, so let's just recall this property here. So if we recall the property, we can just go down here and then write recall the property that L of D, or when you have a function exponential to power nx and then you have u of x, it implies that exponential to power nx L of, I said you are going to add to this d the power of the coefficient of x at this point here. So I'm going to have d plus n, then I have my u of x outside. Right, so from this point here, my u of x here signifies my x cube, while my exponential nx here signifies this. Right, so from this point we can now say that my n is 2, while my u of x is x cube. Right, so using this approach now, we can now use the same method we used here. So we can rewrite this expression by saying 1 over d squared minus 4d plus 2. Then I have my exponential 2x here and I have my x cube at this point. Right, so looking at the rule, let's follow the rules now. I said when you have such expression like this, first thing you do first is to add the coefficient of the power of the exponential, the coefficient of x, all right, which is this. All right, so from this question, the coefficient of x here becomes 2. So you add anywhere you see d, you add 2 to it. So this becomes exponential 2x, all right, 1 over. So this is d squared. I'm going to be adding 2 to d here, then square it. And I have d plus 2 all squared. I'm still going to have minus 4 into d plus 2. And I have my plus 2 here. Outside, I have x to the power 3. Right, so at this point, I'm going to open up this bracket here. I'm going to be obtaining exponential 2x into 1 over. Right, so this becomes d plus 2 and then d plus 2 because it is appearing twice at this point here. So I'm going to be having minus 4 into d plus 2, then plus 2. Then outside, I have my x cubed here. So from this point, I will be having exponential 2x here, then 1 over. So d times d here gives me d squared. Right, d times d gives me d squared. D times 2 here gives me plus 2d. This times this here gives me plus 2d. Right, so 2 times 2 here gives me 4. Then I have minus 4 times d gives me 4d. I have minus 4 times 2 here gives me minus 8. Then I have my plus 2. Outside, I have x to the power 3. So at this point here, exponential 2x becomes 1 over. Right, so I have my d squared. So from this point now, I have 2 plus 2, 2d plus 2d, which is going to give me 4d here. I have plus 2 plus I have 4 minus 8 here gives me minus 4. Alright, so this becomes 4. Alright, so let's just drop this minus 4 first. I have minus 4d. So 4 minus 8 here gives minus 4. Then minus 4 plus 2 gives minus 2. So this is minus 2. I have x cubed here. So 4d can cancel out here. I'll be obtaining this and this is gone. So I'll be having exponential 2x into 1 over d squared minus 2. Then all outside x cubed. Alright, so let me write the bracket here, all this inside this bracket to obtain exponential 2x into, this is also the same thing as having 1 over d squared here, then minus 1 over 2. Right, outside I have x cubed. So from this point now, you observe that the expression here is the inverse. All right, is the inverse. At this point now, you no longer differentiate here because you have a function here. You have to multiply this first. So let's multiply this. Let's use this x cubed to multiply this expression. So I'm going to be obtaining x to the power 2x into 1 over d squared, then x cubed, then minus 1 over 2x cubed here. So if you notice very well, I have 1 over d squared, which I said earlier that when you have the inverse of the d operator, you integrate instead of differentiating. Right, so looking at this point here from the initial one we did, at this point now we had only d, not the inverse. That's why we differentiated to get this. So from this point now we are having 1 over d squared. 1 over d squared. So take note, 1 over d squared is an inverse of d. So at this point here, we are going to be integrating. Right, so we are going to integrate twice here because it's having squared 1 over d squared. So this is exponential 2x into 1 over d times 1 over d of this expression, x cubed, minus 1 over 2 x cubed. So I'm going to be obtaining exponential 2x into 1 over d. So let me integrate this first. So if I integrate x cubed, I'm going to be having x to the power 4 all over 4. Right, so I'm going to add 1 to the exponent of x here, then divide it by the addition of it. That means I'm going to add 3 plus 1. I'm going to add 1 to 3 to give me 4. And I'll divide the expression by 4. That is what I did here. I have minus 1 over 2 x cubed. Right, so I'm still going to differentiate again because I still have another 1 over d left. So this will give me exponential 2x into, so if I differentiate the I'm still going to integrate again. So if I integrate this expression, because it is having an inverse operator d, 1 over d, so I will integrate this expression. I will have x to power 4 plus 1 here gives me 5 over 5 times 4. Right, so 5 times 4 here, then minus 1 over 2 x cubed. Right, so exponential 2x into, right, so I'm having x to power 5 over, right, so 5 times 4 here gives me 20, so this is 20, then minus 1 over 2 x cubed. Right, so this becomes the answer to the expression. Right, so far we've introduced the operator D method. This is just an intro of it, so that when you get into using the operator D to solve the non-homogeneous ODE, you won't get confused. Don't forget, when you have a D, you you differentiate. But when you have the inverse of D, you are going to integrate. Right, so following the properties given above, when the properties I've given you, it becomes very easier for you to solve. Right, so before you solve it, you have to record the property so that it will become as easier as possible for you to tackle. Right, so in our next video, we are going to be using this operator D to tackle the non-homogeneous ODE. Right, we'll be using it to find the y particular, that is the particular integral for the non-homogeneous ODE. Don't forget to hit the subscribe button to get more updates and more videos that are loading concerning this particular topic. Right, thank you.